All right, so just a reminder, we're going to skip the rest of 4.4. It's not 4.4 is not a ton different from section 4.3. We've added a few more dimensions of things to look at when you're analyzing functions. If you want to go look at the slides, though, I did finish them for 4.4 if you want some extra practice. So we're going to move on to section 4.5. This is all about optimization, which is one of the really important applications of derivatives. Something you'll see in future math classes and classes, within your major. Basically, what you're trying to do is you're given some kind of situation that has inherent constraints or limitations to it, and you're trying to find either the best case or worst case scenario, given what you have. So, really, it's pulling a lot of things together that we've been doing for large chunks of the semester, but we'll do a few examples of that next couple of days. Just a warning. So I think I made the homework due Wednesday. There's something there. Okay. Also, I'll be posting a quiz today. That'll be due a week from today. All right, let's get into it. So, first situation here. We have a farmer who has 2,400 feet of fencing and wants to fence off a rectangular field. So 3 sides of that area will be fenced off, and the other side will back up to a river. So I want to find out what's the largest field he can make using this situation. So let's do this first. Let's at least draw what we're trying to talk about. So got a river. I'm going to build some kind of rectangular field. So this is basically what I'm trying to do, and I'm trying to maximize this area in here. So how can we start modeling this situation that I'm asking about mathematically? Okay, so I have 2,400 feet of fencing. How is that going to play into? How can I find the perimeter in this case? So usually it would be length plus width, and then you double that, right? I don't think that's going to work in this situation. Because remember, so my perimeter really all comes down to basically what the maximum that perimeter can be. It's actually going to be more than regular. Because my perimeter is in this case, yes, the perimeter itself is going to be 2 times the length plus 2 times the width. But what do I need to take? What do I need to consider in the way this is written? Elizabeth? It's bordering the river, right? So let's do this. Let's label this as the width. This side will be equal, right? And this will be the length. So if I want to model it that way, the perimeter I'm really looking at is just going to be 2W plus L. Because it's not really the perimeter I'm worried about, it's how I'm going to use this fencing that I have. So this right here, this is kind of this is what we're going to be constrained by. So we're trying to find a maximum area. Why do we have limits? Because of this amount of fencing we have. Is there anything else we can say about this perimeter equation that we just wrote out? Sebastian? Right, but isn't that what this thing is saying right now? If I add that, there's 2W plus L. What's the largest method? It stands to reason that if I want to make the largest possible area, I really should use everything I'm given. So that's going to be part of this problem. What am I really trying to maximize though? How can I talk about the area? Or how would I calculate that here? Just length times width, right? Does that change given the fact that I have one side of this backing up to a river? No. Okay, so here's what I have. I have my constraint equation, and I have my the thing I'm trying to optimize. So basically, I'm looking at this area, and I really want to find its maximum. Now that I have an equation to look at. Think about the way we've been finding maximums or minimums in any kind of extreme value, Sebastian. Eventually, which one of these two equations would I need a derivative of? So I want to find the maximum perimeter. No. So yeah, I want to find the maximum of the area. So I need to differentiate this. But there's one thing I would like to do before I take a derivative. And we have dealt with equations where we have many variables. I'd really like to get this down to one variable. Is that something I can do? I heard a yes. How can I do that? Why would I make all sides equal? So I could do that by making all the sides equal, but that might not give me the maximum area. Right. So this perimeter equation, here's the nice thing about perimeter equation. We got really use an equation that I have. That tells me the fencing I have and what I'm limited by. So for my perimeter, I can do this. The length is equal to 2400 minus 2W, which means I can rewrite my area as this, as a function of width. So that's equal to 2400 minus 2 times width times width. And I will simplify, and then we can stop and talk about where all this stuff came from. So 2400 width minus 2 width squared. Any questions about how we've gotten to where we are so far? Sebastian? Yeah. Calculate area. I'm multiplying that by. So this right here is all. What did we say area was equal to first off? Length times width. So really, I'm using that new expression we have for length. So now I have a function for area that is written in one variable only. So I can take a derivative of that. And keep in mind what we're looking for. Keep in mind what we want to learn about the area. I'm going to take the derivative, so that's going to be 2400 minus 4W. What do I want to do with that derivative? Yeah. So I want to find the maximum area, right? So if I want to find the maximum area, Seems like we all gravitated to that new. Where right. So the big idea I was looking for was critical points, right? Remember, critical points are where local extremes might happen. So if I set this equal to 0, then I should get a unique W value of 600, right? We should also ask, is there any way that derivative might not be defined? Now, it's a polynomial. It's going to be defined everywhere. So I have W equals 600. So that's going to be a critical point. It could be a local min. It could be a local max. Is there a way for us to find out? For us, like, we want it to be a maximum. How can we find out that it is for sure? Okay. So if that made sense to you, awesome. But for completion, let's throw this number line on here. So I'm looking at A prime, and I'm looking at values of W. I know that 600 is a critical value of W. So let's look at what's a good value to look at on the low end. How about 0? 0 and 1 are always useful if you have access to them. If I plug in 0 to the derivative, I get 2400, right? And if I plug in 1000 for W, I get negative 1600. So what does that say about that point there? The local max. So that's our best case scenario. So our max area when we were asked for the dimensions, right? So we want a 600 foot by what area? If we said our width was 600 feet, how long is this field? How do we know 1200? Yeah. So I mean, you can look at the diagram and kind of reverse engineer it. So you get this 600 by 1200 foot area. That's the largest one you can make. Any questions so far? All right. Let's look at the 3D one. So I'm going to make a cylindrical can, and it has to hold 1 liter of oil. I want to find the dimensions that will minimize the cost of the metal needed to manufacture it. All right, so what would you like to do first? Let's draw a bad cylinder. Doesn't need to look good. I just need it to represent what I'm doing here, right? So here's a cylinder. What do I know about the cylinder? What do I care to know about the cylinder? What jumps out at you from the description here? Go ahead. Okay, so why are you keying in the surface area? Why is the surface area the thing to optimize? Yeah. Yeah. So if we minimize this, so we're trying to minimize the amount of material we're using, right? So I haven't given you anything like the top and bottom are thicker than the sides or anything. We're just going to assume that, yeah, it's uniform thickness. So I really want to minimize the material. I mean, I could make this thing 30 feet tall and make it really narrow so it holds exactly 1 liter, but that's probably going to be really expensive. So we're going to try to look for this minimized surface area. Oh, terrible. So if we're going to minimize the surface area, we should probably have an equation for the surface area of this kind of thing. And before we even think about doing this equation, we should probably think about what variables we're looking at. So I drew a cylinder that's actually pretty good. What features of this cylinder do I need to be focusing on? I'll make it even bigger. So one thing you've told me is that we're looking at the surface area. So think about what things you need to know to find surface area. So height's good. Did I hear radius as well? Go away, Banner. And then we're looking at the height and the radius, right? So can we find the area of a cylinder in terms of those two things? Surface area. What shape are the top and bottom of this thing?
Circles.
Circles. How do you find the area of a circle?
R squared.
So part of this area is going to be 2 pi r squared. So I have a circular base, or circular top, circular bottom. What shape is the other side going to be?
Rectangle.
Perfect rectangle. How do you find its area? 2 pi d? Okay. Yep. So yeah, so the length is going to be whatever the circumference of the top and bottom are, and the height is the height. So this right here is the thing we want to optimize this. We want to optimize this. And we're looking for a minimum. What are we limited by? We're limited by the volume. So constrained by volume. How do you find the volume of this kind of shape? So I'll give you in general, if you have a prism, which is what this thing is, because it's base times height, because the definition of a prism, just from probably way back, is if any three-dimensional shape where no matter where you were to slice it, it would make the same cross section. Yeah, it's just the area of the base times the height. So pi r squared h is the thing we're constrained by. One thing I would like to suggest to make this easier to think about is I'm going to replace 1 liter with 1,000 milliliters. And I'm going to remind you of this fact. 1 milliliter is equal to 1 centimeter cubed. So that'll help us think about this in a more efficient way. So this volume is going to be equal to 1,000, right? All right, so now I have a function, or it's a function. It's not a very usable one yet, but I have a function I'm trying to optimize. I have some kind of relationship for how this is going to be limited. How should I unite these two things together? Get the same variable. So here's the thing. In my area function, area is a function of radius and height. I would really like us to get this into a function of one or the other. So which should I go for? Should I try to eliminate the h, or should I try to eliminate the r's? Yeah, that's going to be, could do both. Eliminating the h is going to be much simpler. So I'll solve for h over here, and I got 1,000 over pi r squared. So that means now I can write my area in terms of radius as 2 pi r squared plus 2 pi r 1,000 over pi r squared. This simplifies a little bit. 2 pi r squared plus 2000 over pi r. Oh, thank you, 2000 pi over r. Yeah, no, pi is not squared. All right, now we're good. It's Monday for all of us. All right. All right. So now that I have this function, this is the thing I want to optimize. So what do I need to do? So let's take a derivative. So I got 4 pi r. And what's the rest of it? Yep, minus 2000 over r squared. Okay, what do I want to do with this derivative? Set it equals 0. So remember, if I'm trying to optimize, I'm looking for those critical points. So set this equal to 0, solve it, and I get 4 pi r equals 2000 over r squared, which gives me 4 pi r cubed. 2000, which gives me this. I'll keep it exact for now. So it should be 500 over pi. And that all cubed. Go ahead, Sebastian. Yeah, we'll try again. So now that I have that critical point, what do I care to do with it? So why are we plugging it into the volume equation? I think we plug it into the volume, we're going to find height, right? Okay. We can do that. So the good thing about us having solved for height earlier is we can use it in that form to get this even stranger looking number, 500 over pi to the power of 2/3. All right, are we sure that we have our dimensions that minimize the cost here? And there's one thing we should probably do. We should need to make sure it's the minimum. So how do we make sure it's the minimum? Let's do something different. The number line's always for you, but I want to remind you of something else we can do. I'm going to take the second derivative of our area. So it'll be 4 pi plus 4,000 over r cubed, I believe. Yeah. So one thing we talked about it briefly a little while ago, that if you have a critical point, the second derivative can tell you what kind of critical point it is. So what is happening and now that I'm realizing what form our R value is in, let's stick with it. So a double prime of the cube root of 500 over pi is going to be equal to 4 pi plus 4,000 over 500 over pi. Do I really need to calculate all this out, or is that enough? I believe that's enough, but why is it enough? Positive, right? All I'm doing is adding positive numbers together. So since that's positive, what does that tell us about our critical point? Yep. So yeah, because it's concave up, it's decreasing to this value. Which means it has to bottom out at a minimum. What, Sebastian? Is it this little smudge right here? That's a mistake. It was just me scratching. So minimum surface area. Dimensions are, I'm also going to box them in. So this radius and this height. Well, anything else before we move on to another one? All right. So I want to find the point on this parabola that is closest to 1, 4. How would you like to start? You could plug those in. It's not, that equation is not going to be true. So what we're doing here, we have a parabola, and we want to know, basically, we got to find the point on the parabola. Yeah, we're going to do a distance. Let's first draw what everything looks like. So here's our parabola. So yeah, I'll give, for example, I know the point 1, 1 is on this parabola, right? You can plug those things in and verify. I'm trying to find out how far I am from this point 1, 4. So I already know that my distance is going to be at most 3, right? There might be something closer. Okay. What was that? Oh, yeah. What am I doing? What am I doing? All right. Not y squared equals x. X equals 1. That's not going to be a nice integer, is it? Okay. X equals 1. Oh, X, yeah, okay. That's good. So the point 2, 2 is on this graph where how far we're trying to minimize our distance to 1, 4. So we had a vote to set this up as a distance. What would that look like? Minimize distance. So can I write an equation or some kind of function for distance here? Okay. So I'm going to start here. I mean, if I want to find the distance between 2 points, I'm going to zoom out of this picture a bit here. This is 1, 4, right? This is my XY, my mystery point I'm trying to find. If I set this up like this, I really have some X distance and some Y distance. So, I mean, I think Probably at some point, most of you memorized the distance formula, but really that distance formula is just based on Pythagorean theorem. So my question here is this: I want to square. So d squared is equal to something squared plus something squared. So one will be a horizontal distance, one will be a vertical distance. How would I find my vertical distance?
Subtracting 4 from.
What kind of value on the function? You want to subtract 4 from what? X or what? So if I'm looking for my vertical distance, I really need to know how far I am above or below 4, right? So I'm going to compare y and 4, and I'm going to compare x to 1. Any questions on this thing? So we have the thing we're trying to optimize. We need to look at the thing we're trying to constrain. Like what's limiting?
The parabola.
Yeah, both. If we were just trying to minimize our distance from 1, 4 with no other like requirements, we could just choose the point 1, 4, right? But we need a point that's on this parabola. So then we have a good distance equation, and our constraint is going to come from the equation of the parabola. Y squared equals 2x. So I would really like to get this distance equation. I really want to get this distance equation to look like what? What do I want to change about it? Or can I just jump into the derivative now? That's all. Right. So yeah, the thing I'm trying to get you to see here is that if at all possible, and it almost always is possible, get so now that we have this, I can change our equation to this: d squared equals y squared over 2 minus 1 squared plus y minus 4 squared. All right, so now that I have this, what do I need to do with it? So that's one thing I want to ask you. I can take a derivative here. Does it bother anybody the fact that the left-hand side of this is d squared? Or are we okay to work with that? So that's one question we can ask. Does it need to be squared?
Yeah.
Yeah, so it's all based on. So right now, we have a different. So we could take the derivative now, or we could square root the whole thing. I think it's probably easier if I just take the derivative as is. What variable am I taking the derivative with respect to here? Y. So I'm going to take the derivative of y with respect to y of both sides. What's the left-hand side going to look like? Yeah, dt dy equals. I'll let you take this one. It's a little more complicated than the last couple. How'd you get 4y? So let's think about what we have to do here. So let's just focus on that left set of brackets. That y squared over 2 minus 1 all squared. What kinds of things do we need to be looking at when you take a derivative of that kind of object.
Chain rule.
Need a chain rule, right? So what's our outermost function if we're looking at chain rule there? X squared. So derivative of that is going to be 2 times the parentheses, right? But then what's the rest of the chain rule say I have to do? What's the derivative of the inside? Yeah, just y. All right, so that one is done. How about the other one? Should be 2 times y minus 4, right? All right, so I have a derivative. So what? Yeah, so now that I have this derivative, here's one thing I can do. Everything is doubled, right?
Yeah.
That makes me happy. That's one way to simplify. Keep in mind though, now that I have a derivative, so yeah, I can do this. I heard that we want to divide by d as well, so we can do this. dd over dy is equal to y squared over 2 minus 1 times y plus y minus 4 all over d. What do I care to do with? So what do I want to do with this derivative? What am I trying to learn about the distance, or what am I trying to do with the distance? Yeah, the derivative doesn't really, there's nowhere else it can go. We haven't taken any other derivatives. We don't have any other functions that relate the distance to anything. But let's just go back to basics. We're trying to find the point on the parabola that is closest to some other point, 1, 4. So what am I trying to do with this distance? Trying to minimize it. Trying to find the minimum. So I'm trying to find the minimum of this distance function. I have the derivative of this distance function. So how would I start looking for those minimum values? Yep. So I'm looking for critical points. If I'm trying to find a minimum or maximum, I'm looking for critical points. And something kind of nice here, if this thing's equal to 0, then what I'm really setting equal to 0 is the numerator. So I have y squared over 2 minus 1 times y plus y minus 4 equals 0. Now we just got to simplify and solve. So that's 1/2 y cubed minus y plus y minus 4 equals 0. So 1/2 y cubed equals 4. Yep, then we get y equals 2. So the point that we just kind of talked about randomly is the closest one. So we got y equals 2. What does that mean that x is equal to? Also 2. So the point that's closest to the point on the parabola that's closest to our, that other point, 1, 4 is 2, 2. Yeah, so y equals 2. We already had this equation. X equals 2 squared over 2. Any questions here? All right, so let's talk about what we've done so far. So before we move on to another example, let's just kind of break down the process. So not only what we did with this question, but with the previous two, what do we think is a good way to start? Yeah, so determine what you are trying to optimize. That's a good first step. What else have we done?
Then you draw a situation.
Yeah, draw a picture if you can. I think it's almost always a good idea to do that. Draw a picture. If possible. All right.
Situation.
Okay. So find equations. To model the situation. So yeah, you're typically going to have at least, one thing that constrains the situation. And one thing to optimize. All right, now what?
Variable.
Yep. Simplify what? What equation am I trying to simplify? Simplify optimization. Good. How do you find critical points?
Taking derivative.
Do that first. Take derivative. And find critical points. All right, so I have a derivative. I found critical points. So I found the places where the derivative, just spelled wrong. So after we found those critical points, what do I do with them? Yeah. Make sure they truly optimize
Situation.
Yeah, so break down the word. What is, like, what optimum or optimal, what an optimist is. Yeah, you're looking for the best. Finding the best case. Anything else we need to think about in terms of like things like just reflecting on this process, or is this pretty complete? Yeah. Oh, I didn't have the room for that. Right, the complete solution. So whatever I actually asked you for. I think that's pretty complete though. So any questions on this or any of the three examples we did? We got a couple left. I don't think it's a good idea to start either one of them with just a few minutes left. All right, I'm gonna go ahead and stop there. A little bit early.